Everyone to this week's TADS seminar. Today we are very happy to have Dr. Hongfeng Yu giving a talk. Hongfeng, he is a faculty at University of Nebraska-Lincoln, and he is also an interim director of Holland Computing Center there. And Hongfeng received his Ph.D. from University of California, Davis, and after that he was a postdoc researcher he spent some time in Sandia National Laboratories. And his main research interests are in big data analysis, visualization, and high performance computing. And today, Hongfeng is going to talk about large graph visualization. Okay.
Yeah, thanks for introduction. So my work is focused on the high performance computing, visualization, and data analytics. And so given the scope of the research for this seminar, so the topic wise, so I selected the topic about my visualization work. So today I will introduce our work on the edge bundling for large graph visualization. So in this talk, I will introduce the motivation and the background of this work, and then introduce some of our work and to address the performance and accuracy and evaluation question about the edge bundling for graph visualization. Okay, so first let me introduce the motivation for this work. And graph visualization, essentially, you have been perceived in every day. For example, like the gene code expression network. And typically we can express a network as a matrix. But once we're using visualization, for example, like this graph visualization, then people can easily see, right? There's a two cluster in this graph, which is very difficult to directly perceive from the matrix representation. So graph visualization has been widely applied in many areas. So for example, like social networks. So I just borrow the social network visualization from the Facebook. And in the software engineering, they also have the function call network to indicating the relationship between the modules in a software system. And in the eye tracking system, they're also using the graph visualization to show the eye track pathways. And one typical way to visualize the graph, as you see many examples in the textbook, is a noding diagram. So the visualization is very intuitive and straightforward. So basically, you have a circle or the node to represent the vertices of a graph, and then you can use the edge to represent the connection or relations of the network. So this is very simple and intuitive. But this noding diagram also have the problem. So it can be easily generate a visual clutter. So for example, this diagram essentially showing the US airline graph. And with a certain number of the edges, then the graph the visualization become very visual clutter. And essentially it's very difficult for us to perceive any information from this visualization. So to address this issue, people developed a set of algorithms called the edge bundling. So the basic idea of edge bundling is very simple. So visually, we just bundle the similar edge together. So in this case, then we can use a few number of the pixels of the bundles to highlight the structure of a graph, and we can significantly reduce the visual clutter. For example, in this diagram is showing the edge bundling result for the same graph. Then we can clearly see where the hub, for example, Denver or the San Francisco or the LA, you can clearly see this hub point in this network. And meanwhile, you also clearly can see the graph structure in edge bundling result. However, edge bundling also have several challenging aspects. So first one is typically they are computationally expensive. And it takes a quite long time, like a couple seconds or 10 seconds to generate edge bundling visualization for a reasonable size of graph data. And also another open question is how can we evaluate the result of the edge bundling? Okay, so to address these challenges, let me first revisit the general edge bundling framework. So the edge bundling framework typically starts from the noding diagram, okay? and from our traditional straightforward visualization, and then go through the edge bundling process. And then the third step is just render the edge bundling result. And during the edge bundling process, typically there's 3 steps. The first step is generate sample points of the edge, and then we measure the similarity among the samples. And then we move the sample points to the new position. And typically this is an iterative process. We need to go through multiple steps to generate suboptimal graph layout. So here I just revisit a classic algorithm called the force direct edge bundling. So this is a representative algorithm showing the process of the iterative process. So assume we have an input graph. So here I just show 3 edges and 6 vertices. So the first step is the sample edge. So assume we just put the sampling point in the middle of the edge. And this algorithm using the two force to measure the similarity among the samples. The first is the spring force. Okay, so basically, essentially, is around the edge. Another one is the electrostatic force across the edge. Okay, and using this model, then we can mimic the similarity or the similarity between the sampling point. And then using the calculated force, then you can imagine there's a spring, right, to pull this point together. Then we can move the point to the new position. And then we can iteratively apply this process. So in the next iteration, then we can generate a new sample point and calculate the new force and then move to the new position. So this is just an example with the 3 edges. And here I show you the result using a real-world airline data set. So this is the original noding diagram. Okay, so basically with a certain visual clutter. And then after 10 iterations, then we already can see the edge has been bundled together and form the curves. And then through the later steps, then we can see more clear bundle has been formed. So this is a classic example of edge bundling. And then you can see the complexity of this algorithm typically is SE square I plus IE. So S is the sampling point, and during the step to calculate the similarity, then the complexity is E square, because you need to compare the sampling point across every pair of the edge. And certainly, so for each iteration, you need to compute this similarity. And then IE represents the sampling step. So in every iteration, you need to generate new sampling point. Okay. And this essentially increases the computational cost when we have a large number of the edges. So to address this performance bottleneck, so we propose a set of technology. So the first one I would like to briefly introduce is using hardware acceleration to enable web-based graph edge bundling. So in this work, we propose a new technology called pixel-based edge bundling. And this algorithm can achieve high parallel efficiency for intensive edge bundling computation. And it is also highly portable for most devices. So this algorithm can enable the edge bundling on desktop or mobile device and achieve interactive speed for a relatively large graph. So the basic idea of this algorithm is using multi-thread to parallelize the edge bundling process. And we assign each thread to do the sampling edge, computing similarity, and moving the sampling point to the new position. And we use a matrix represent the position of the subdivision point. Okay? And so here assume we have n lines and we have m points of each point. Then the basic process of this algorithm is trying to upgrade this matrix and corresponding to the position of each subdivision points at the same time and during each refinement iteration. And given this matrix representation, so we can easily carry out the parallelization of the edge bundling algorithm. So assume initially we just fill the endpoint of the edge into this table. So this is represented as the orange dots in this matrix. So each point represents the position of the endpoint of one edge. Then in the first iteration, then we generate the first subset of the subdivision point. And for each division, then we can calculate the force corresponding to their neighbors. Okay. And you can see the calculation of the force applied to each individual vertices can be computed at the same time. So given this representation, we can see it is relatively easy to implement using the multi-thread techniques, either using the multi-thread CPU or using GPU. For example, you can easily implement this algorithm using the CUDA, and you can assign one CUDA thread to calculate the calculation in each entry of this matrix. But it is non-trivial to implement this algorithm on general purpose GPUs. And the reason is direct GPU memory read and write is not universally support. And often the mobile device, like our iPhone, iPad, are often equipped with the low-end GPUs. So in order to address these technical barriers, we propose a pixel-based texture bundle. The basic idea is we still employ the matrix data representation of the force direct edge bundling. And we utilize the texture functionality of the OpenGL or WebGL to encoding the position, essentially encoding the matrix. Then we still using this texture on matrix and main structure, and then using the texture to encoding it. And then the next question is how can we update the texture according to the new position of the subdivision point? So in this case, we're using ping pong buffer. So here I just skip the technical detail about the ping pong buffer from the GPU. But the basic idea is we're using two textures to represent the same matrix. And the matrix is updated through the rendering process, so which is indicating using these arrows. So during the rendering, then we can update the back texture using the front texture. And in the next generation, then we just swap the buffer. And then the front texture can be updated by the back texture. So in this case, then we can update the texture and the corresponding matrix by moving the position of each subdivision point to the new position. So here I just skip this detailed GPU implementation details. And here we can see the visual result of the new algorithm. So here we test our algorithm on a desktop. So this is Intel Core i7 CPUs with a NVIDIA GeForce GTX 1080 GPU. And we display the algorithm using the Chrome web browser. So here's the result of the US airline dataset. And the top one showing the noding diagram. So certainly we can see severe visual clutter. And using our algorithm, then we can clearly see the structure of graph clearly. And so this is an even larger data set, and it's close to 0.5 million of edges. And if you're still using the traditional noding diagram visualization, basically you cannot see nothing from the visualization result. And using our pixel-based edge bundling algorithm, then we can highlight the main structure of the graph and reduce the visual clutter problem. And in terms of performance, so we also calculate the rendering time of this algorithm. So we use 3 data sets, US Airlines with 2,000 edges, and also the France airline with 17,000 of edges, and the large US migration data set, it is 0.5 million edges. And the rendering solution is 80 by 80 images. So we compare the different algorithms, existing algorithms, including the force direct edge bundling on the CPU, and using the CUDA, as well as using the JavaScript-based implementation. And also we compared with other like a web-based implementation, like a Mingo, which is a JavaScript version of the edge bundling, and fast Fourier transfer edge bundling, which is implemented using the CUDA. And then we can see across all the algorithm, our pixel-based edge bundling algorithm can achieve the lowest amount of rendering time. For example, like the US airlines, and we only have the 5 milliseconds to generate the framework, to generate the result. And using the CUDA, traditional CUDA-based implementation, it needs 100 millisecond. And for the large US migration data set, and the traditional CPU-based algorithm cannot generate the result. And our algorithm only take about 100 milliseconds to generate the result. And more importantly, our algorithm can be used on the mobile device as well. So we also do the performance testing on a tablet, on the Google Nexus 9 tablet, and which has a Kepler GPU. And we test the two data sets. One is the US airline and another one is the France airline. And you can see on the mobile device, our algorithm also can achieve interactive frame rate for this relatively large graph. And you can see the existing JavaScript-based method either cannot directly render the large airline data set, or it will take about a significant amount of time to generate the result. Okay, so in this work, we introduce pixel-based edge bundling, so which is a web-based framework, and we're using OpenGL, WebGL functionality to accelerate the edge bundling using multi-thread techniques, but through the relative low-end GPU. And we can achieve high quality visualization, which is comparable to the other algorithms. But we achieve the interactive frame rate on the web-based platform. Okay. So in this work, we're using hardware acceleration to enhance the speed of the edge bundling. But you can see the fundamental algorithm complexity is essentially about the same. And you can see we still need to take the in particular here we have the E-square component in the complexity. So the complexity would be still high with respect to the edge numbers. So to further reduce the complexity or increase the performance of edge bundling, another set of edge bundling algorithm has been proposed called the kernel density estimation or KDE-based method. So around this direction, the representative algorithm have the KDEEB, kernel density estimate graph bundle, and the CUBU, which is CUDA universal bundling, and the fast Fourier transform edge bundling. And the basic idea of this KDE-based algorithm is rely on the image-based sampling. So given a noding diagram of a graph, the first step is to conduct image-based samples. So basically, we get a set of sampling point of the previous noding diagram, and let's just zoom into this small area. So assume this is a set of sampling point with this tiny area. So assume we have about 8 sampling point, and the basic idea of this kernel density estimation-based method is trying to move this point to the local optimal position. So one example is using the k-mean clustering, and then using the kernel density estimation and to estimate the central point of the local cluster. And then they generate the gradient-based advantage to move the sample point to the new location. Okay? So in this case, you can imagine all these sample points around the different edges will be merged into a few locations. Okay. However, if we direct apply this idea, and the visualization can incur the excessive converged artifacts. So basically, essentially, if you direct apply this method, then you can easily generate this straight line kind of patterns. So this is the result. Okay? And in this case, then you can generate this kind of web-based the graph or the grid-based artifacts about the result. Okay. To address this issue, so the typical method is to resampling the result and to iteratively do the conversion. Okay. So the basic idea is after we apply the mean shift to move the sampling point to the new position, then we do the image-based sampling again. So we need to do the resampling again. Then we do the mean shift and do the iterative refinement. So this is this example showing this pipeline by the kernel density estimation. So through this method, then we can reduce the convergence artifacts, and then we can generate a very smooth edge bundling result through the kernel density estimation. And in this case, then you can see the complexity has nothing to do with the edge number. So you can see here the original E square has been removed, and the whole complexity is dominated by the sampling point. Okay, so basically, you only need to move the number of the you only need to move the sampling point, and the complexity is only need to deal with the number of the sampling point. But meanwhile, you still have this component here. So at each iteration, so I is the iteration number, and E is edge number. Then you need to do the resampling. You still need to resample each edge. So that's introduce the second term. And you can see once the edge number is small, so this term can be ignored. But in the real world, once we have a large number of edges, then we can no longer ignore this term. So to address this issue, so we propose a new algorithm and to further reduce the complexity of the edge bundling. So our approach is based on the moving least square approximation. So we call this edge bundling is a MSEB. So edge bundling using moving least squares. And we introduce the moving least square into the edge bundling, so we can simplify the existing edge bundling pipeline and to ensure the scalability and efficiency of the edge bundling. So we show the result can, our algorithm can be applied to a range of the 10,000 to 500,000 of edges. And meanwhile, we also propose a GPU-based implementation. Okay. So given the general pipeline of the edge bundling, so the innovation of algorithm is to use the moving least square to move the sampling point to the new position. And this new strategy can remove the step of the resampling. So in that case, we can reduce the complexity of edge bundling. So moving least square has been widely applied for reconstructing contiguous function from a set of unorganized point sampling. So this is a classic method for like the 2D curve reconstruction, as well as like the 3D surface reconstruction. So once you have the 3D point cloud, and the moving least square algorithm is typically applied and to generate the surface reconstruction. So in our algorithm, we leveraging the moving least square to move the point to the new positions. So let's still to go back to this airline data set. So once we have noding diagram result, then we generate a set of sample point, and we still focus on this small area. So assume we have this set of the 8 sampling point, and then we assume there's an implicit skeleton. So that is a curve or the bundles which is suitable to place this sampling point and then help us to form the bundle. Okay. And the skeleton can be interpreted as a piecewise curve. Okay. So in order to construct the skeleton, we're using the moving least square. So for each point, sampling point xi, and we form a radial neighborhood hi. Okay. And then we using the least square approximation to calculate the local curve fi, and using weighted least square error, and we're trying to minimize this term. So in this equation, the first term is the least square optimization, and the second term essentially is the Gaussian function to express a weighting between the points. Okay. So by minimize this equation, then we can form a local piecewise polynomial curve fi. Then we can project each point into this new position on the fi. So then we can see the difference between the moving least square based method and the kernel density based method. So we can see both methods is trying to move the local sample point to the new position to represent the centralized bundles. And the KDE based method needs to iterative resample the result to avoid the excessive convergency problem of the artifacts. And using moving least square, then we only need to sample the edge once. Then all the sampling can be iteratively moved to the new position using moving least square. So basically, we don't need to conduct the resampling in order to address the convergence artifacts. So by compare the complexity between these two algorithms, you can see the KDE-based method, it needs to do the resampling in every iteration, but we only need to do the sampling once. So we remove the I in this term. So this is our result using the moving least square based method. So the first data set is a small US migration graph. And here we use the three algorithms, moving least square, our method, and a fast Fourier transfer edge bundling, and the force direct edge bundling. And this table showing the total time sampling point involved in this algorithm. And we can see the moving least square requires the lowest number of samples, and also they have the lowest time to generate the result. So we can see in order to generate this diagram, we only take about 0.38 seconds. And the rest of the algorithm, for example, like a fast Fourier transformation-based edge bundling, take more than 12 seconds to generate this result. And this is another data set. So France airline data set, it has the 17,000 edges. And again, so using our method, we only take the sub-second to generate our result. So we can see that given the lower complexity, the real time generated in this the forerunning algorithm also can be significantly reduced. So this is a large US migration graph. So it contains 0.5 million of edges. And again, so our time is only 1/4 of the fast Fourier transformation algorithm. And more interestingly, so our algorithm can generate a more smooth result. Okay, so the edges are more smooth around the patterns of the US migration. But the fast Fourier transformation intends to generate this grid type or the mesh type of the layout. And visually, so our visualization result is more meaningful and to showing the direction of US migrations and across the different cities. Okay, so our method is simple and efficient and can construct edge bundling for relatively large graphs. And the method only need to sample edge once, and we avoid the resampling in the following iterations. And then this method can ensure the scalability and the efficiency. And so I introduced the two methods through the hardware acceleration and reduce the complexity to accelerate the edge bundling algorithms. But essentially, during the previous, when I show you the previous slides, you already see the different visualization result from the different edge bundling result algorithm. Visually, maybe they also very can generate appealing result. Then the question is, which visualization result would be best? And the question is, how can we recommend the visualization and their parameters to the users for the different applications? So this essentially leading to a question is, how can we evaluate the different edge bundling algorithms? Okay. And unfortunately, there's still a lack of the comprehensive evaluation, and it is difficult to decide which algorithm is better through the visual perception. And it is also very hard to select the optimal parameters. And as you see in the previous slides, the visualization result are also affected by many factors, like the number of iterations, number of sampling points, and also the size of kernels. And how can we suggest the users to select the optimal parameters to generate the result? So we propose information theoretical framework to evaluate edge bundling to address the gap between the visualization algorithm as well as their practical usage. Okay, so this framework essentially is based on the uncertainty quantification in the edge bundling visualization. So here I just using a simple graph to illustrate our idea. So in this work, we only consider simple paths, okay, of a graph in this study. So basically, we only consider the simple edge between the two vertices rather than consider complex paths across the edges. Okay, so assume here we have a adjacent matrix to represent the graph. So the 1 means there's an edge between the vertices I and j. So for example, v1 and v2 has vertices. And if there's no any edge, so we just fill 0. Okay. So this is a traditional adjacent matrix representation of a graph. And then then we can directly translate into a noding diagram by visualizing this matrix as in this B. Okay. And still, so we can see there's 6 vertices, and we can easily see the connection or the relation between the vertices. And then we apply the edge bundling algorithm. So assume the C is the edge bundling result we generate from this noding diagram by bundle the different edge together. Okay. So then essentially this leading to some ambiguity for us to understand this graph. The basic question is, in the B, clearly we can see there's an edge between V1 and V2, and there's no edge between the V3 and the V2. But after we generate the edge bundling result, then there's a question. Is there any edge between the V3 and the V2, right? Is there any edge between the V3 and the V4 or V3 and the V6? So essentially from this visualization, we can count how many paths would be possible connected or connected between the two vertices. Then we can generate this matrix A based on the edge bundling result. So in this case, we can see V1 and V2 still have the edge, right? Connect them. So we fill 1 here. But meanwhile, we also can see the V3 and V2 also have the path or the edge in this diagram. So we also fill the V2 and V1 in this matrix entries and put a 1 here. So then we can generate a matrix indicating how many edges between the two vertices from the edge bundling visualization. And certainly given this matrix and the edge bundling, and the users might have the different interpolation of this edge bundling result. For example, users might interpolate the matrix of the edge bundling into this graph, because users might thinking there's an edge between the V3 and the V2, and the V3 and the V4, and the V5 and the V4, and generate the result of this. Alternatively, they also can interpolate this this edge bundling result into this graph. And clearly, we can see this essentially involves certain misunderstanding of the original graph. Then the question is, how can we quantify this misunderstanding or the uncertainty encoded in the edge bundling visualization? So we're using 2 metrics to evaluate the edge bundling. The first metric is called the coverage. So the basic idea is very simple. So how accurate the graph rendering or the visualization can represent the original matrix. So A represents the original matrix, and there's a edge bundling graph, so represents the matrix we generated. Then we can compare every entries in these 2 matrices and to get a coverage rate. So certainly a high coverage rate means the result of visualization can have a better representation of the original graph. But certainly this is just 1 metric. And we can easily see once we have the high coverage, but this not necessarily leading to the meaningful visualization. So I will show you the result later. Okay. So in the second matrix, we build based on information theory in visualization. So this diagram showing the relationship between the data and the visualization. So the red circle represents a random variable, or you can regard the data. So this circle represents the entropy of the information held by the random variable. And this green circle represents a visual description of the data. And certainly it also contains the amount of information. And the intersection between these circles are the mutual information, and which means the information shared by both U and O. And this component essentially the conditional entropy. So this represents, given the visual representation, how much of the original data still unknown. Okay, so given the relationship between the visualization and data, so certainly we want to maximize the mutual information between these two circles and to minimize the conditional entropy. So next, let's see how can apply this concept into the evaluation of noding diagram, or evaluate the edge bundling. So we propose the second metric is based on the information theoretical framework. So basic idea is, given the y, so which is a visual description of the relation between the two vertices I and j, and x is the relation between the two vertices, and then the question is, if we are given the visual representation between the two vertices, how much conditional entropy we can obtain from the visualization. So we form this. We model this conditional entropy using this equation. So where the Aij essentially is the number of the edge we can formed in the visualization between the two I and j. Okay. So essentially we can reduce simplify this equation into this very simple log2 formula. Okay. So let me just using this simple example to illustrate this equation. So basically, we assume we have a very simple edge bundling result. So we only have the V1, V2, and toward the V6, we have the 6 vertices. And so we want to measure the visual uncertainty between the V3 and the V4. And we can see there's 2 paths, right, between the V3 and the V4. Okay, P1 and P2. So the corresponding matrix entry is 2. But given this visualization, essentially there's 3 possible cases for us to interpolate the connection between the V3 and the V4. There's one path, P1, or another path, P2. The third possibility is there may be any connection between the V3 and the V4. So all the possibility is 1/3. Then we plug this number into the previous equation, then we can see the conditional entropy is 1.58. Right? And alternatively, we can give a relative more complex graph, edge bundling result. And we want to measure the visual uncertainty between the V3 and the V4. And now we can see there are 3 paths between them. And then we can see the conditional entropy to encoding the uncertainty between the V and the V3 is increased to 2. So which means the visual uncertainty has been increased if there's more paths between the 2 vertices. Okay. So intuitively, this is can be easily see using this relative complex noding diagram visualization. So this is, I already showed this is noding diagram of a large US migration, and it is very visual cloud. So we just random pick 2 vertices, VA and VB. So essentially, the visualization cannot help us determine if there's any path between the 2 vertices, given the high conditional entropy value. So basically, there's many paths allowed us to connect the VA and the VB. Then it is very difficult for us to determine what's the detailed relation between the VA and the VB from the visualization. So then after we calculate the conditional entropy between the 2 vertices, then we denote the total uncertainty of a visualization as W. And the amount of the uncertainty, then we can simply just the summation of the condition and entropy for any pair of the vertices. And some practical challenges we have, it is non-trivial to get number of the edge to connect to vertices in visualization. So it requires a computational method for us to approximate the edge or the path number between the two vertices. So we develop a path funding algorithm to calculate the possibility of the path to connect to vertices in real visualization. So the first step, we're using the region growing to find the possible region to connect the pixels. For example, given these 2 pixels, orange and purple one, then we're using region growing then to generate the possible paths. Then we're using min-shift class to classify this path into the different region. And for each subregion, then we found the number of paths, build a graph, then using depth search to find the possible paths between the target and the source region. Okay, so next we apply this algorithm to compare the different visualization algorithms for the real world data set. So for example, here we have the US airlines, then we use the moving least square edge bundling, force direct edge bundling, and the fast Fourier transfer edge bundling. And for each algorithm, then we apply the different parameters. Then certainly then we can see, we can generate different visualization. Then the question is, how can we evaluate this visualization result? And through our metric, so we introduced two metrics. So one is the coverage, so which is represented in this graph as a horizontal axis. So from the 0.8 to the 0.9, and which means all the visualization has a good coverage about the original noding diagram. And the vertical essentially is uncertainty, and the high number represents higher uncertainty. Okay? And we're using different color to represent the different visualization algorithm. So purple, red is the force direct edge bundling, and the blue is the fast Fourier edge bundling, and the star represents the moving least square edge bundling. And for each algorithm, we have different parameters. For example, for the fast Fourier transfer edge bundling, we adjust the kernel size, and for the moving least square, we adjust the compact support. And for the force direct edge bundling, we adjust the compatibility threshold. So this leading to the different visualization. And for each visualization, and we computed its uncertainty and its coverage, and we plot into this diagram. And from this diagram, then we can see, so within the range of the coverage larger than the 85%, and the uncertainty is less than 0.75, we only have two methods left. Okay, so this essentially corresponding force direct edge bundling as well as the fast Fourier edge bundling. So this is corresponding to this result. So from this comparison, visually we also can intuitively see for some for the bottom graph, we can see essentially the graph is oversimplified, so they leading to the less coverage. And meanwhile, the top one also have the more edge. Certainly it gets a good coverage, but it also involves more uncertainty when the users to interpret the connection between any points through the visual representation. And these two visualization provide the best result among all the result. So we also compare the visualization result for the US migration data sets as well as large US migration data set. So we visually, so we can see completely different visualization result. Then we also project them into the 2D diagram, and we can see the fast Fourier transfer function edge bundling can give us a good coverage as well as a low uncertainty. And meanwhile, if you look at this diagram, and you will see the noding diagram essentially here, right? So the noding diagram, as I showed the example previously, so you can see it has a really high coverage. Essentially, it is a very visual clutter and essentially covers all the possible edges. But meanwhile, it also introduces high uncertainty. So basically, any point between any 2 points, then it is very difficult for us to interpret if there's any edge or the path connecting these two vertices. So that's why the noding diagram, although it can provide a good coverage, but it also increases the uncertainty significantly for the large graph. Okay. So in this talk, I revisited the edge bundling algorithm. So it is a very important visualization algorithm for the network visualization. And it can significantly reduce the visual clutter problem and also clearly show the highest level graph structures. But unfortunately, it is traditionally computationally expensive, and it is non-trivial to evaluate different edge bundling algorithm. So in this talk, I introduced two of our work. The first one using the hardware acceleration to increase the efficiency of this algorithm. And the second one, we introduced the moving least square algorithm to further reduce the complexity of the edge bundling. And meanwhile, we also use information theory to propose an evaluation framework to compare the different edge bundling algorithms. Okay, so with this high performance edge bundling, essentially can leading us to some more interesting applications and given the interactivities. So one example is we developed the tweezer, which is a visualization of tools to display the correlation of weather and the tweeters. And so in this visualization, so we build the web page. Okay, so this is currently what you see is a screen capture of a program running on the web page, and given our high performance edge bundling algorithm, then you can see we can achieve the interactive rendering. You can user can interactively zoom in, zoom out, and see the detailed network structures of the data set. So in this diagram, let me just in this diagram, so we build the correlation between the Twitter people's sentiment of the emotions and the weather. So on the bottom map, we grab the Twitter data and running the sentiment analysis to see people's emotion. So the green means that people are happy. Oh, by the way, we run the sentiment analysis with respect to the weather condition. So the green point means that people are happy with respect to the weather, and the red dots mean that people feel unhappy with respect to the weather condition. And on the top level, then we have we're using a layer to indicating the temperature distribution. And then we're using clustering algorithm to classify the temperature into the different regions. And here you can see that we have more Twitter data from the Omaha and also some from the Lincoln, but the less Twitter data we obtain from the west of Nebraska. And then we build the correlation of people's feeling with respect to the temperature. And so here, in the previous example, I almost show the 2D graph edge boundary result, but in this example, you can see this also can be applied to the 3D visualization. And you can see this essentially is during the summer, and the most area covered by the Nebraska is a relatively low temperature, and people generally are happy when the temperature is low during the summer. But here using during the Omaha and the Lincoln area, and you can see the certain unhappy emotion is related to the high temperature. All right, so in the future, we would like to visualize the extremely large graph. So in this talk, we only demonstrate the visualization close to the millions of edges. And in the next work, we're trying to visualize the billions or even larger number of the edges. And we want to leverage the graph analysis algorithm, such as community detection, and to create a more effective visualization for the extremely large graph. And apart from the theoretical model, we also want to conduct a user study to evaluate the different graph visualization algorithms. Okay, so I would like to thank NSF to provide funding support, and also my team to conduct this work. Okay. All right, thank you for attending this talk, and I'm ready for any questions. Thanks.
Thank you very much, Hongfeng. I think we have time for a few questions.
Just can I ask a few clarifying questions? So
sure.
You talked about the regression technique, which seems to be the same as the local polynomial regression, or what we usually call the LOS, the local scatter plot smoothing. Is that the name that is used by computer scientists, or is that slightly different?
I think the basic idea is about similar, but maybe so the moving least square algorithm is heavily used in the computer graphics community for the surface reconstruction.
So it's just a different name, I guess.
Yeah.
So another thing, as you basically addressed part in the latter half of your talk, when you do this kind of bundling, sometimes you could create an impression that maybe there's no link, but you could create an impression of a link there.
Yes.
Sometimes there's a long distance link in the traffic, air traffic example. Maybe there's a lot of traffic from New York to Los Angeles, but you basically see kind of like a local path. It's not clear whether there is a direct link over long distance or not.
Yes.
That do people think about ways to address those kind of issues? That
no, currently is I think this is also the challenging problem in the graph visualization. So when the number of link is small, right? So it is very easy. You can control the rendering of each individual edge. Then you can see if there's a path or no path. But when we apply the visualization algorithm for the extremely large graph, and then the challenging aspect is we only have a limited number of the pixels. And then the question is, how can we allocate these pixels on different edges? So edge bundling essentially is an algorithm to make the trade-off. So we bundle the edges and to get the better usage of the pixels. But essentially, then it will generate the confusion, right? Do we have the edge or between the any two vertices? Yeah.
So basically, it's a compromise. There's no clear.
Yeah. No, this is because this is compromise, because currently, fundamentally, we only have the limited display space. Think about even we want to display this large graph, right? Millions of the edges or the billions of edges on our mobile device. Then how can we handle this this issue? Yeah, this is essentially
more useful than the direct connection of that. That's just a math. Nobody can see anything.
Yeah, right.
Yeah, thanks.
Yeah, thank you.
I have a question. Actually, that was kind of motivated by the discussion just now. During the talk, I kept wondering whether the algorithm has any notion of a loss function. I think towards the end of the talk, you actually talked about the evaluation part. I think kind of is kind of answering part of the question, which is there's some uncertainty-based evaluation, right? Mm-hmm. So one question that I kept thinking during talk was, so this is the research is motivated by visualization.
Yes.
But to me, there is a related issue, which is not exactly which is related to visualization, but not exactly visualization, which is somehow regularizing the graph to basically simplify the graph, yet preserving the semantics.
Yes, exactly.
Right.
Yes.
So I mean, are these two sides of the same coin? Are they sort of not exactly the same thing?
No,
I think I'm happy to see the evaluation, but your algorithm didn't seem to be motivated by optimizing some sort of semantics preservation.
Yeah. So
right.
So if so one type of algorithm essentially is I'm not sure is like the kernel density based algorithm. The kernel. Let me see. Go back to so basically the so people's. I'm not sure if this answers the questions, but a kernel density based algorithm essentially given this graph, right? Then how can you just locally group this point, right? So the basic idea here is given a set of point, then locally you just to generate the representative point. So this is similar to the clustering algorithm, right? But if we direct apply this algorithm, certainly we can just merge different edges into a few points, right? So basically you can generate this straight line, but essentially you will generate this pattern. But underneath, so they address these issues and applying the resampling algorithm. But during the each iteration, essentially they apply the mean shift clustering algorithm to try to group the similar sampling point into a few number of the cluster, and for each cluster then just using one point. So that in that case then to reduce the number of points. Yeah. So I think also I didn't mention in the first algorithm we also using clustering algorithm to group the edges according to according to the certain measurement.
Yeah, thanks for that clarification. I mean, look, clustering is essentially, I don't know whether people would agree with my statement. I mean, clustering is essentially a heuristic algorithm, right? So you basically group things that are similar together.
Yeah.
So there's not a clear notion of a loss that's being optimized here.
No. Yeah.
But when I think about this kind of problem, there needs to be some notion of a loss that needs to be optimized.
Right. I agree. So in the visualization communities, researchers also trying to develop these algorithms, but still there are several difficulties to how can we design these loss functions, and to generate the. So, but the basic question is: given the graph, is there any ground truth of the edge boundary result? According to the current effort in this community, there's tons of the research, tons of the visualization result through the different algorithms, but nobody claims this is the ground truth. Yeah.
I think one way to think about it is to say, what do you do with the graph, right? You know, visualization is one way to do it, but there might be some other things you can do with the graph. Let's say you can achieve some task based on the reduced graph, then the reduction is meaningful.
Yeah, we're also doing some like a graph community detection, and in that case, I agree with you. So we have the certain loss function to evaluate the community detection result. But here's for the visualization. So yeah, certainly. So currently, still, it's very difficult to define what is a ground truth, right? Yeah. Thanks a lot. Yeah. For the.
Thank you very much, Hongfeng, for the nice talk. So I think that concludes this week's TADS seminar. So see you all next week. Yep. Thank you.
Yeah, thanks a lot. Yeah.
Yep.
Bye.
Thank you.
Thank you.